Welcome back. We're going to take a look at section 7.2 in this video, which specifically deals with sampling distributions for sample proportions. So a couple symbols that I want you to get really comfortable with. P hat. I won't say P hat very often because that doesn't have meaning. I'll refer to that as the sample proportion. And then P is the population proportion. So this is a sample statistic, and P, since it's a population parameter, or P is a population parameter is what I'm trying to say. All right. So let's take a look. So sampling distribution of P hat, or the sample proportion. So in this scenario here, you have this huge vending machine that has 45% of the candies in it are orange. And actually, it is probably worth bringing this up. Reese's Pieces, which are amazing candies in my opinion. All right, so we want not number, we want proportion. So if let's do 50, that'll work out better. If I randomly select 50 candies from this vending machine, oh, we don't need to animate, it's going to take forever, and figure out what percent are orange. Wait for it. Hey, 44%. There it is. If I do this again, 38%, 38%, 52%. This is sampling variability. Each sample is going to yield different results. Now, let me just throw a whole bunch out here. Let's do 96 more, bring it to an even 100. Okay, so this is an approximate sampling distribution. I can start to figure out what the mean and standard deviation are. I could see that the mean is pretty much centered at the true mean, so this is unbiased. If I keep doing some more samples, you can see I'm getting closer to this true parameter. So this is unbiased. Then I can start to look at how likely it is that I get a random sample of 50 Reese's and I get 20% orange. Well, if I got 20% orange, that's not happened at all so far in the 484 samples we've drawn. So I might think something's wrong, the machine's broken, it's not really 45% orange. So a couple of things to think about. All right. So the sampling distribution for a single sample proportion. And you'll notice some scientific notation. What am I saying? Some specific notation here. The mean for the sampling distribution is mu sub p hat. It's the mean of the sample proportion is equal to the real proportion, the population proportion. The standard deviation, sigma sub p hat, is equal to this. In terms of, does this make sense? As the sample size increases, the variability is going to decrease. There are some conditions that we're going to start to check. Because we're sampling without replacement, and I don't want to get too far down into the weeds here, something called this 10% condition needs to be satisfied. Basically, your sample size is less than 10% of the population size. And you're trying to see, is your sampling distribution approximately normal? Because we want to use that density curve to start calculating probabilities. The way that we check that is we check something called the large counts condition. Do you have at least 10 successes and 10 failures? If you do, then we say yes, the sampling distribution is approximately normal. All right, so take a look at the check your understanding, pause the video, give it a go, come back when you're ready. So 75% of adult internet users watch videos online. We survey a simple random sample of 1,000 young adults and calculate the proportion. This, again, is the sample proportion. So what is the mean of the sampling distribution? Well, we did a simple random sample of 100. This should be unbiased, so it should be centered at the true value, the true proportion, the population proportion. So it should be centered at 75%. So let's talk notation. The mean of all the sample proportions should equal the true population proportion, which is 75%. And that formula is on your green sheet. I don't have a green sheet right in front of me, but I'm 99% sure on that. Find the standard deviation, just substituting into your formula. Notice it's P, so you're using the true proportion, the 75%. So the standard deviation is a little over 1%. I can calculate that if the 10% condition is met. Well, is 1,000 less than 10% of all internet users? Yes. Yes, it is. Or I can do 10 times 1,000 and say there's more than 10,000 young internet users in the world. Absolutely. Is this distribution approximately normal? Now I'm checking that large counts condition. Do I have at least 10 successes and 10 failures? Well, if I'm sampling 1,000 people and I expect 75% of them to watch videos online, that would be 750 yeses, and 25% not to, that would be 250 no's. So yes, this is met. They're both at least 10. If the sample size was 9,000 instead of 1,000, what would change? Well, as sampling size increases, the variability decreases. This is increasing by a magnitude of 9, but since it's under the square root of 9 is 3, so the standard deviation would be 1/3 the original size. 1/3 the original size. Now, if what I said doesn't make sense, you can always plug in the 1,000, plug in the 9,000, and divide those out, and you're going to see you're going to get 0.3 repeating. It's 1/3 the size of what it used to be. If the sample size was 4,000 instead of 1,000, then the standard deviation would be half the size. If it was 16,000, standard deviation would be 1/4 of the size. So now looking at using the normal approximation. So now we will start to answer questions like, what is the probability that 35% of first-year college students attend a college within 50 miles of their home? All right. So if I know that 35% do, I want to be within 2 points of that. So I want the sample statistic to be somewhere between 33 and 37%. So what I need to do is find the mean and standard deviation of the distribution. Just what we did on the previous page. The mean is equal to the true mean. Standard deviation, as long as the 10% condition is met, it is. They go through that here. Is the sampling distribution approximately normal? If it's not, I can't use normal CDF or anything like that, so I need to check the large counts condition. I'd expect 525 students to go away to college far away and 975 not to. Those are both at least 10. Then what you're going to notice is just our old friends, the z-scores, calculating z-scores using normal CDF from the negative 1.63 to the 1.63, 0, 1 to get the area under the curve. Anything talking about table A, ignore that. We do our calculations on the calculator. We don't use the table. So, all right. Moving along. Summarizing. So when we're describing the sampling distribution, we're talking about center, the mean, variability, which is the standard deviation, and shape, is it approximately normal? And the way that we can tell that is to check the large counts condition. And for the standard deviation, we're checking the 10% condition. All right, there's one more part of this section that's actually from chapter 10 that I want to talk about. It's when you have two proportions that you're comparing. And we look at the simulated or the sampling distribution for two proportions. So say we have a group of males and a group of females that we're looking at. Individually, we would have just what we have. The shape, check the large counts condition for each. The center, they should be centered at the true value. And then the variability, you'd have your standard deviation formula just for each. But now we're combining them. So this goes through kind of how to use the random variables that we just learned about to do that. We know from Unit 6, we can just, if I want the mean difference, I can just subtract the means. So in this case, I would subtract the two means and get whatever that difference is. And I know from last unit I can add the variances. So if I do that, if I take my standard deviation formula and square it, I'd end up with this. but I want the standard deviation. So I'm going to take the square root of that whole thing. So this formula comes from doing the work with the independent random variables that we had. So you're going to be looking at two main formulas. The mean difference, just subtract the two means, and the standard deviation of the difference, you're really adding the variances and taking the square root. That has not changed. So this summarizes it pretty nicely. To find the mean difference, subtract. To find the standard deviation, add the variances, take the square root. The reason these aren't squared is because they were originally under the square root. Let me see if they have a check of understanding before I go too much further. Nope. Okay. So let's just look at this bottom question that they have here. Okay, teacher brings 2 bags of colored goldfish to class. One bag has 25% red and the other bag 35% red. So each bag contains more than 1,000 crackers. So we take a simple random sample of 50 from bag 1 and 40 from bag 2 to see. And they want to look at the difference. Well, the shape, do we expect to have at least 10 red crackers and 10 non-red crackers out of our sample of 50 and 40? That's checking the large counts condition. Notice we're going to have to check this twice. Once for bag 1, successes and failures, once for bag 2. So we have 4 numbers we're checking to see if they're at least 10. They are. That means the sampling distribution is approximately normal, which means we could calculate z-scores and so on and so forth. Find the mean. That's just, they're both unbiased, so they should be centered at that true value, 25 and 35%. I'm just subtracting those. Negative 10%. That just means there's a higher proportion of red in bag 2. The standard deviation. Now I'm checking the 10% condition. 50 times 10. There's at least 500 crackers in bag 1. 40 times 10, at least 400 crackers in bag 2. 10% condition is met. So I can go right to calculating the standard deviation by plugging in, I'm adding the variances essentially. So to get that standard deviation of about 0.09. So at the end of this section, 7.2, you should feel comfortable setting up a sampling distribution for a proportion, knowing the symbols. P hat is the sample proportion. P is the population proportion. And once you have it set up, determining the center using the formula for the mean, the shape using the large counts condition to see if the sampling distribution is approximately normal or not, and the variability using the standard deviation formula. You want to be able to do that for one proportion, which was from section 7.2, and then for the difference in proportions, which is what I just covered. So I hope this was of use to you, and I hope you have a nice day.